Einstein's own view was that the basic concepts and laws of physics, what I'm calling the fundamentals, are, quote, in a logical sense, free inventions of the human mind. He elaborates this view in these statements that I have taken from his book, The World as I See It. Since, however, space perception only gives information of this external world of physical reality indirectly, we can only grasp the latter by speculative means. The theoretical scientist is compelled in an increasing degree to be guided by purely mathematical, formal considerations in his search for a theory, because the physical experience of the experimenter cannot lift him into the regions of highest abstraction. The axiomatic basis of theoretical physics cannot be an inference from experience, but must be free invention. There is a rather general tendency to believe that Einstein and the other architects of modern physics could not have been as casual about the foundations of their system as these words would indicate, that they must have been tied into something, anchored to something solid somewhere. But that's not true. As Rudolf Carnap puts it, they were constructed floating in the air, so to speak. Einstein gives us enough information about the origin of his own theories to make it clear that when he talks about free inventions, he means free inventions, nothing else. For instance, the propagation of electromagnetic radiation plays a very significant part in his theories. And the comments that he made about the theory that he invented to account for that propagation have a considerable bearing on what we're talking about now. In one of his books, he goes on at considerable length about what a difficult problem this is. And he concludes with this statement: our only way out seems to be to take for granted the fact that space has the physical property of transmitting electromagnetic waves, and not to bother too much about the meaning of this statement. The point of all this is that all invented theories share this same defect. They are all mathematically correct, but they are all conceptually wrong, not because of any errors in the construction, but because of their inherent characteristics. Now, this statement may seem to be in direct conflict with a great many of the confident assertions that we find in present-day scientific literature, which tell us that the validity of present-day theories has been established beyond any reasonable doubt. But if you look at the evidence in support of those assertions, you will find that it is all mathematical. What has been done is to establish that those theories are mathematically correct, just as I have said here all along that they are, because of the way they were constructed. But those theories that are mathematically correct are not unique. None of them is. In every case, there are other theories that are also mathematically correct. And as Richard Feynman tells us, we can't distinguish between any two of them on any on any scientific basis and say which is correct. Because, as Feynman says, they both agree with experiment to the same extent. So two theories, although they may have deeply different ideas behind them, may be mathematically identical, and then there is no scientific way to distinguish them. Now, Feynman goes on to say this: every theoretical physicist who is any good knows 6 or 7 theoretical representations for exactly the same kind of physics. What Feynman does not say is that those statements apply only to the present day and other day inventive theories. They do not apply to inductive theories. Those theories that have been derived by induction from factual premises. For example, the kinetic theory of gases is a theory that relates the gas laws to the motions of the particles that compose the gas. Now, no one tells us that he has a half a dozen equally valid representations for what the kinetic theory tells us. In fact, there's not another one alternative, because the kinetic theory is an inductive theory that's tied into the facts both mathematically and physically, so that it's both conceptually and mathematically correct, whereas the inventive theories are correct mathematically only. Now that raises an interesting philosophical question as to whether there's actually any net gain by using these inventive theories during a period when we would otherwise have no theories at all to account for some important physical phenomenon. Actually, we don't need them. We could equally well use the mathematical relations that we have without any theoretical explanation. So the whole thing boils down to a question as to whether there is any better to have a wrong theory than no theory at all. Now, there's a very widespread belief that that's true, that it is better to have a wrong theory. It dates back at least to Francis Bacon. The idea behind it is that a plausible theory, even if it's wrong, may suggest some lines of inquiry that in the end will be productive. On the other hand, we know that continued adherence to the Greek inventive theories, particularly during the last few years of the Greek ascendancy, was a very serious roadblock in the way of scientific progress. And we have pretty good reason for believing that much the same is going on now. In any event, the fact that needs to be recognized at the moment is that we have again arrived at the kind of a situation that existed in the Middle Ages. The present-day inventive theories have accumulated too many epicycles. And at the same time, inductive theory has caught up with observation and experiment, so that as we enter the 21st century shortly, we are in a position to go back from the inventive theory to a solidly based inductive theory again. Now, the imminence of such a change could be deduced simply from an examination of the times involved in the cycle of reversals that I've been talking about. The first inductive theories lasted for thousands of years before they were overthrown by the Greek inventive science. Now that, the first of the inventive sciences, endured for 2,500 years before it met its fate at the hands of Newtonian inductive science. The accelerating pace of science is shown by the fact that in spite of its greatly superior character, the science that's normally associated with the name of Newton only lasted for 400 years before it in turn succumbed to the second inventive science. Now, if we consider the same rate of acceleration, we can see that since another 100 years have passed, that we are about due for another reversal will take us back into an inductive theory. But we don't have to depend entirely on inferences of that kind, because there's plenty of direct evidence to show that we are again in the same kind of a situation in which Greek science found itself during the Middle Ages. In the first place, the accumulation of epicycles has reached the point of absurdity in a great many cases. The quantum theories, for instance, have a long history of one ad hoc modification, interpretation after another, until it's very questionable now if the theory is even intelligible. In fact, Richard Feynman, who I've already quoted a couple of times, says it isn't. Feynman says this: I think I can safely say that nobody understands quantum mechanics. The situation in the field of atomic structure is much the same. The favorite pastime there these days is inventing properties for the elusive particles called quarks. Now, nobody has seen or otherwise observed a quark, or anything that could be a quark. In fact, the most urgent problem for the theorist right now is to invent some theory by which it can be said that the quarks are inherently unobservable. But nevertheless, we are told just what kind of quarks can exist and what their properties are. Such interesting properties as color, charm, and so on. In order to fit this situation into the proper perspective, let's bear in mind that not only are the quarks themselves unobservable, but the particles that are supposed to be constructed out of quarks have never been observed either. Now, it's true that those particles are given some familiar names, such as electron, for instance. But the hypothetical electron, constituent of the atom, has a totally different set of properties from the observed electron. And there's actually no adequate justification for calling them by the same name. The same is true of the other hypothetical constituents. The hypothetical neutron constituent of the atom, for instance, has to be stable, whereas the observed neutron is very much unstable. The truth is that there is no definite evidence that the atom is constructed of particles at all. Now, that may seem to be rank heresy, but a great many of our foremost scientists have said the same thing in different words. For instance, here's Erwin Schrödinger. Once we have become aware of this state of affairs, the epistemological question, do the electrons really exist in these orbits within the atom, is to be answered with a decisive no, unless we prefer to say that the putting of the question itself has absolutely no meaning. Here we have a good example of the difference between induction and invention in the construction of a theory. And since I'm making this my principal point, I want to elaborate on it a little. Such men as Newton and Einstein were very much aware of that difference. Newton insisted time and time again that he did not resort to invention. Einstein, on the contrary, criticized Newton for trying to get his theories inductively. And I'm afraid that a great many people do not recognize the difference because they both start